Talk about hidden Markov models today. Last time we were talking about Markov models. We didn't quite get to hidden models yet. So this was a Markov model for a CPG island. Okay? Or actually, since we haven't put any probabilities in here, this is a Markov model for any sequence, and depending on what probabilities you put onto the edges, it'll change what kind of a Markov model it is. But this was for the purpose, we started this for the purpose of studying CPG islands, that is, places in the DNA where you have high concentrations of the dinucleotide CG, okay, which tends to indicate that you're upstream somewhere of a region that has genes, or maybe you're into the region that has genes. Okay, so as a Markov model, we can think of this as a generator of sequences where you just start somewhere. Actually, in the notes that I'm passing, they have a begin and an end state. So the begin takes you randomly to one of these A, T, C, or G states, and then the end takes you randomly to a place where you've finished the generation. But the point is that if I start somewhere, let's say I start in this C. This is a state, by the way. And every state emits a character. So in this representation, this C state emits the character C. Okay? Big surprise. And then, depending on the probabilities that will be written on these arrows, it will flip a coin, and depending on the probabilities, determine which arrow to follow. It could follow the one that takes it back to the C state, in which case you'll emit another C, or it could take this arrow over here and emit a T, and so on. And so, as I was saying last time, what's the big deal is just a little pictorial representation of thinking about generating random sequences. As you're walking around here, you're emitting a symbol at each step, moving to some other state or perhaps the same state, emitting the next symbol, and so on. And so why have we gone to such lengths to formalize the notion of successively emitting or generating one symbol after another? Well, if you put different probabilities on the edges, you get different Markov chains, Markov models. That is, the actual walk, by the way, through this thing is called a Markov chain. This thing itself is called a Markov model. And by putting different probabilities on the edges, you get different behaviors of this particular Markov model, and you get different Markov chains out there as different probabilities. And the probability that you're in any particular state at a random point in time changes and is influenced by the overall probabilities here. So some very nice theorems about Markov chains that let you relate the probability structure to the expected, or the probability that you're going to be in any given state. But we don't need that. What we need here is what we want is to use this model to try to distinguish between those segments of DNA which might be CPG islands and those that might not. And so we use basically dinucleotide frequencies that are known in CPG islands and those that are known to be outside of CPG islands. And so in the notes that I'm passing around, on page 50, you have the plus model. That's the CPG data. So looking at sequences that are inside a CPG island, you have dinucleotide frequencies A, C, G, and T. I'll just put a few of these up here just to give you A, C, G, and T. So 0.18, 0.274, 0.2 426, and 0.120. Okay? So what this is saying is that 18% of the time, when you have an A, it's followed by an A, if you're in a CPG island. Okay? 27.4% of the time, when you have an A, it's followed by a C. 42.6% of the time, when you have an A, it's followed by a G. And 12% of the time, when you have an A, it's followed by a T. And all the other data, I'm not going to write it down, but it's in that table, but it has a similar meaning. Okay? Similarly, you have dinucleotide frequencies outside of CPG islands. Okay? And that's also another table, ATGT, ATGT. And those frequencies are presumably different. Otherwise, you'd have no hope of identifying, at least in this kind of approach, whether you're in a CPG island or not. So just for illustration, this one is 0.3, 0.205, 0.285, and 0.210. So it's, well, you have to compare these ones. When you're outside, A followed by A is more common than when you're inside of an island. AC, roughly, well, this is more common, but not by a huge amount. A followed by G, AG is more common inside a CPG island than outside, and similarly, AT is smaller than AT when you're outside, okay? And if I did this right, both of these rows should add up to 1. Together, they should add up to 2. So now, actually, from a modeling standpoint, where you get this data is a little problematic. Where you get CPG islands from, well, I mean, it's CPG islands. So, but what data you want that's not CPG, there's all kinds of reasons why it is not CPG. I mean, all kinds of reasons why it might be special or different than the kind of anonymous DNA that you might be given where there is some CPG and there's some other regions that are close to it or in the same longer sequence but are not CPG. So that distribution may not correspond to what you're seeing here, but we'll just ignore that particular issue. But you should be aware of that if you're ever going to try to set up some of this, these models yourself. Okay, well then we can take this data and translate it into probabilities for a Markov model for CPG islands or a Markov model for sequences outside of a CPG island, or we could set up a log odds model which would relate the ratio of those two, the log of the ratio of those two. And so we'll see all three of those things coming up in some of these applications. But how do let's just say I want a Markov model for a CPG island. What's the obvious thing to do in terms of turning these frequencies into a probability? Actually, these things, I mean, these look like probabilities to me. Okay? So there's something in these notes here that's got a slightly different notation where they're taking the ratio of counts. But anyway, once we have these observed frequencies, these look like perfectly good probabilities to me to just put on the edges. So from the A transition, A to A should be 0.18, and A to C, 0.27, and so on. Okay. So we can set up, put the appropriate probabilities on this model, and then given a sequence. So let's say I'm given a sequence CCTG, then all I have to do in order to find out what's the probability that this model generated it is just to take the product. I start here C, take the product, take this probability from C back to state C, whatever that probability is, and then from C to T, whatever that probability is, take the product of those probabilities, and then T to G, and the product of the probability of what I have with what's on this edge here. And that gives me the probability that this particular sequence was generated by this Markov model. And I can do that for any particular sequence. Okay? So similarly, I can have a Markov model for the sequences that are outside of a CPG island. And given any particular sequence, I can calculate its probability as well. All right. So what I really am interested in, though, is discriminating if I have a long sequence or I have a given sequence. And I want to know, and here it is, and I want to know, is it probable that this is from a CPG island? Well, we've discussed how you approach these kind of questions. You're interested in the log odds ratio of that it's from a CPG island versus being outside a CPG island. And so you want to calculate a score. This is sequence X. Okay? You calculate the following thing. Sx equals the log of the probability that that X would be generated given the plus model. So what's the probability that X would be generated by the model for the CPG island, which we just discussed how to do that? You just walk through the Markov chain, multiplying together those probabilities, divided by the probability that X would be generated by the minus model. Okay? And as we discussed earlier, since this is a product, this is ultimately a product, and we're taking the log of the product, it's really better, it's equivalent, but better numerically, to think of this as a sum. And so this is summation log of, AX minus, AX I minus 1, XI, I'll explain this in a minute. That's the plus, A XI minus 1, XI minus, I equals 1 through L. Okay. So I should have told you, I should have introduced this notation. This is what the book is using for the transition probability of moving from state I minus 1 to state I. Okay. States in the Markov chain are identified with the emission, so there's really no ambiguity if I talk about the either the state or the character at that point that's being emitted. So this would be A GC under the plus model. So I have some particular probability here of going from G to C under the plus model, if I'm talking about the plus model. And so since this probability here is the product of A's, and this is a product of A's, when I take the log of that, this becomes the sum of the logs of those particular probabilities. So all I've done really here is write out explicitly each particular probability along that Markov chain. This is the probability of going from the state that we saw in step I minus 1, but that's a particular character. It's a particular character that got emitted in the I minus 1 position to the state that we saw at step I, which is the character that's emitted in step I of the Markov chain. Okay, and then here we have the similar thing under the minus as the outside of the CPG island model. Okay, so the log of the two probabilities is the log likelihood, but this is equivalent to taking the sum if there are L characters in the particular sequence we're looking at. So X has length L, so that's why the sum is there. And then I can take this ratio, actually, I can take this and give that a single name, which is just beta xi minus 1 xi. I equals 1 through L. Okay? Tell me if this is too abstract. I mean, we've done some particular examples. We started with when we talked about log likelihoods, we started with the position-specific scoring matrices and so on. So I'm hoping that this, although this is fairly abstract notation at this point, since you've been thinking about some log likelihood ratios already for about a week, that this is making sense. Is anybody finding this too abstract? Yeah.
So H is only the transition probability from one base to the next.
Yeah. Right, right. And so in fact, what this really is, we have, this is A. You want to think about that. And this one is little AC, and this is little AG, and this value is little AT. Okay? So that's all really, I know this is a lot of notation for what really was a very simple idea. You're just taking the appropriate, in the sequence X, you're taking the overlapping pairs, the tumors, and looking up the appropriate probability from the plus model and the appropriate probability from the minus model, taking that ratio, taking the log of that. But these can already be calculated because there's a finite set of states. There's only 4 in here. So there are only 16 relevant pairs, no matter how long the sequence is. So you could have already calculated all of these ratios and the log of all of those and put that into a scoring table, a scoring matrix. Okay, so that as you move through the Markov chain, you're just adding those scores as appropriate. Okay, other questions? Yeah.
For the first position, what's the probability?
Yeah. Okay. So if we had a beginning state, we would also have the probability of going from it. So here's a start state, and it takes us to any one of these states. And if we know something about the actual distribution of the starts for the plus model and for the minus model, we can put those on these edges. Otherwise, we might just think of it as uniform, in which case it isn't going to affect the overall ratios. But if we do know something about the start then we should put these into there as well. And then we have an additional term in there, which was the probability of going from here to the first symbol in the sequence X. Okay. So actually the notes do talk about starting states as well. All right. And on page 52 of the notes that I showed you, that I passed out, they have a histogram that shows the results for some real data that they ran this model on. And well, first of all, I should tell you what a bit is in this context. Whenever you take the log base 2, and these logs are base 2 here, whenever you take the log base 2 of some number, the units, it's nice to have a name for the unit that you're talking about, and the term that's typically used in this context is a bit. Okay, so, what really is a bit? We know it in a computer. It used to be a physical place that you could either set to 1 or set to 0, or it's a position in a binary number. Okay, but in this context, people talk about bits. It comes from information theory anyway. But operationally, all you want to really think about whenever you see somebody talk about how many bits in some ratio or some sum, all they mean is that somewhere somebody took a log base 2, and at that point the quantity that they're talking about is referred to as that many bits. Okay? Just a name. All right, but the key thing is that they ran sequences that were from the CPG island, and they got out a score, okay, on those sequences. And then they got out scores that were from sequences that were not from the CPG island. And they show you what the scores were. On page 52, you have that histogram in terms of the number of sequences that had particular bit scores. And the ones that are in the dark are the ones that were from the CPG island, and the ones that are in the light are not. And what you can see is that with some exceptions, and there's actually a rather extreme exception down at the left, what you're seeing is that this model gives a larger score, a larger log odds ratio score, which is what you want, a larger bit score to those sequences that really are from the plus model, that really are from the CPG island, and gives negative scores typically to sequences that are not in that model. But there are a few exceptions. So you can see from that plot, from that histogram, that you're getting some false. If you were going to use the bit score to tell you whether or not the sequence, so you have some unknown sequence, you don't know whether it's from a CPG island or not, and you run it through this Markov model, and you see what the bit score is. And if the bit score is up at like 0.3, what should you conclude? Everybody has this in front of you except for the people at home. So pretend this is an exam question. This is a Markov model for CPG island. You have some unknown sequence. You don't know whether it's from the island or it's not. Okay? And you run it through the model. You calculate, you come out with some score SX, all right, which is this derived just as I've explained it here. And it's 0.4. Okay, so previously what you knew about is this histogram. Now what do you conclude? Is it from the islands or not?
There's a low probability. It's low, probably. It won't be possibly from the island.
Okay, yeah. So, what this distribution, what this histogram here is showing you, is that those sequences, that's represented in the dark here, those sequences that really were from CPG islands are getting scores. Most of them are positive 0.1 to about 0.3. So I picked 0.4 to actually be very extreme. That's a very high number. And so it's very far away from the numbers that were typically obtained from sequences that are not in the CPG islands. Actually, maybe it was a trick question because it was so high, it was off the charts. And it's like if I was asking you, after you took the distribution of heights of basketball players and not basketball players, and you saw that typically basketball players had a higher distribution that were in the range, 6 feet to 7 feet. And then I asked you, and what would you conclude about somebody who was 10 feet tall? Are they a basketball player or not? That might be a trick question. Okay, so I probably shouldn't have made it 0.4, but if I had made it 0.3, then hopefully you see that you should conclude on the basis of this kind of model and the use of this model that you're probably in a CPG island. And if I had said you had something that was minus 0.2, you should probably conclude that you're not in a CPG island, or at least the evidence is not strong enough for you to conclude that it is. So another kind of exam question based on this sort of material would be, given this histogram that's in front of you, does this show that this methodology gives more false positives or false negatives? Where the decision variable is the sequence in a CPG island? So a yes, a declaration of yes, when the answer really is no, is a false positive. A declaration of no, when the answer is really yes, is a false negative. Okay? So in this histogram, you don't have an absolute separation of the scores. So here we had, roughly, these are the scores for the when the sequences really were in the CPG island. And then we had, we had some out here, if you'll notice. There's some dark regions out here. And then the minus ones, mostly around in here, those negative numbers with a little bit of light shaded region coming in here. Okay? So these guys, are these false positives or false negatives? And I don't mean it related to this. Okay, the decision question is the sequence in a CPG island? And you say yes. Okay, so if you say yes, so this is the decision, yes and no, and this is the truth, yes and no. Okay, so this is a false positive. Oops. So say yes. Oh no, this is good. Yeah. Decision. If you say yes when the truth is no, this is a false positive. If you say no when the truth is yes, this is a false negative. Okay, and these are the good guys. This is where you didn't make an error. So what is this? False positive or false negative? False negative, yes. This was from sequences that really are in the CPG island, but the score they got out from this model, and the model comes from those numbers that I showed you or that are in the table. That number turned out for some reason, and we're only looking at dinucleotide numbers. Under that model, it turned out negative. It turned out looking much more consistent with the sequences that were not in the CPG island. So you have some false negatives here. This thing in here is a false positive, but not a very strong one, because probably it just depends on how conservative you want to be. If you want to be careful not to make false positive errors, you'd probably insist on values that were in this range, consistent with the rightmost portion. But again, it depends on your tolerance for false positive versus false negative errors. If you can tolerate more false positives, then you'd move this back that way. All right. Okay, so that's a Markov model, and how a Markov model in the CPG example is used to discriminate sequences that are in the CPG islands, likely anyway, from those that are not, and how you would use this as a decision model to try to figure that out. Now, in a Markov model, the key thing about a Markov model is that when I tell you what state you're in at a given point in time, so you're walking through this model randomly or according to those transition probabilities, you're in a particular state. The future states, the probabilities of being in the future, even just one step, where you're going to be one step into the future is, of course, influenced by, in fact, it's completely given by what state you're in right at the moment. But it's not influenced by what the actual walk was, what the chain was in the past that got you to that state. Okay? So the probability of your future behavior in a Markov model is dependent on the present, but not on the past. Anyway, I guess I shouldn't put it that way, because your present state is dependent on the past. Okay? But to calculate the future probabilities, the only information you need is your present state. Okay? You don't need the actual walk that brought you to that present state. Okay? So that's one feature of the Markov model. And the next feature that's important about a Markov model is that if I show you what the emissions were, remember, as we walk around this Markov model, we're emitting characters. And that's the generation aspect of this model. If I have a particular sequence in mind, and then I ask what particular chain it was, that's sort of the flip. That's the dual type question. But as a generator, when you walk around a Markov model, each state emits a symbol. And if I show you the symbols that were emitted, you can tell me precisely what the sequence of states was. Okay? So the outputs in a Markov model, the output identifies the states. Okay? In a Markov model, the emissions, or another way of saying this, the Markov chain itself. Well, no, that's not the right way of saying it. But the emissions identify the chain of states, or the Markov chain. Okay? So, for example, the CCTG, you know exactly what happened. What was the chain that generated that? It's C. If we have a begin state, we moved to the C state, stayed in the C state, went to the T state, went to the G state, and then we would have an end state here as well that you can get to by anybody. Okay? So knowing the emissions tells you what the state was as well. Now, that doesn't mean that each state has a deterministic emission. Let's say at this state, you could emit T or E. And T is emitted with a probability 1/4, and E is emitted with a probability 3/4. I don't know what an E is, but just imagine that we have a different Markov model here. It produces different sequences than the previous one. Whenever you're in this state, you decide which character to emit with a probability 1/4 for T and 3/4 for E. Okay? But this still has the property that if I tell you what the emission symbols were, okay, you can tell me exactly what the Markov chain was. And that's because E is emitted only in this, it's because every symbol, each symbol is emitted only in a single state. Okay, so there's never any ambiguity. On the other hand, if I had here that T is emitted with a probability of 1/4 and A is emitted with a probability of 3/4 when you're in this state, then all of a sudden this is no longer a Markov model because it no longer has the property that just by knowing what the emissions are, knowing what sequence is generated, you can tell me what the series of states, what the particular chain was. Because whenever you see an A, you don't know whether it came from this state or it came from this state. Okay? And so this is no longer a nice little Markov chain. It's what's called a hidden Markov model. This is no longer a nice Markov model. It's a hidden Markov model. So the key thing about what a hidden Markov model is that you imagine that there's some Markov model in a black box. So you can't actually watch the chain as it's happening. You can't see what the state transitions actually are when this Markov chain is generating something. But what you get to see are the emissions. You get to see what characters are being generated. And all you can do is infer, deduce. You can calculate some probabilities of what the actual Markov chain was, what the series of states was that generated that particular sequence. Okay? So I'm saying this in some abstraction. We'll see in a minute a particular example, and we'll see another one next time. But I really think if you go to a typical, just drop in anywhere where people are using hidden Markov models and ask them what a definition of it is, you get 100 different wacky responses. The critical, and particularly you say, well, where does this word hidden come from? What's hidden about this Markov model that we're talking about? And most people will have no clue. Okay, so one of the things I want you to go away with and remember 5 years from now is what does it mean, sort of in general, that a model is a hidden Markov model as opposed to a vanilla Markov model. And the key ingredient, and it says so in these notes that I've handed out, again, is that if you see the emissions, you cannot necessarily say, with complete confidence what was the sequence of, well, you can't always, depending on what the sequence was, sometimes you can. But you aren't guaranteed to always be able to say what the sequence of states was that generated that particular sequence, that particular output sequence. Okay, so to illustrate this, we want to take the CPG island story and make a hidden Markov model for it. So previously what we had was one Markov model for the plus model and one Markov model for the negative model, for being outside CPG islands, and one model for being inside. Okay? And when we had a particular sequence in hand, and we wanted to know, should we conclude that it's inside an island or it's not, then we use this log odds ratio idea. But a hidden Markov model will try to combine both aspects, both models, into a single model. And so what you have in a hidden Markov model this is again for CPG islands, is you'll have the Markov model up here for the plus case, for the island, or in islands. And I didn't replicate it, but up in this box should be all of this without the start and the end. But all of the, going back to here, with the appropriate probabilities on these edges for the plus model. And what you have down here is the Markov model with the appropriate probabilities for the minus model, for being outside. And what you have between them, and I didn't write all of these, are edges that take you from one side of the model to the other or back. So when you're in the A state of the minus model, you can move to the A state of the plus model as you moved from a region in a sequence that was not in a CPG island to one which was. So you have an A not in a CPG island followed by an A, if you take this one, to an A that is in the CPG island. Okay? And then we similarly have a transition backwards. Or you can have from this A to a C or to a G or a T and all the ones backwards. And imagine we have a similar thing from the C and the G and the T here. So it's a very, very messy picture. And you can see that on page 52 also. Okay? So now, where do we get the probabilities for this model? We want to put probabilities on the edges. And where do we get those from? Okay, this model, when I've put both together, is in a sense a more predictive, a better model than having each one separate, because now you have a way of incorporating transitions. If I have sequence data like this, where this is in island, and this is out, so this is plus, minus, minus, and here we have some plus, and so on. So you have sequence which shows you not only portions of the sequence that are outside of CPG islands, but you also see transitions, AC. Now, I don't know that the transitions are that sharp in the real biology, but it's nice to think of this in that way first, just to clarify the model. So here you would have data where you're going from an A that's in the minus region to a C that's in the plus region, okay? And therefore you can compute the probability, the fraction of time that you go from an A that's in the minus to a C that's in the plus, and also the fraction of time that's in the minus alone or in the plus alone. And by using that data, you can get a probability of transition from the minus model to the plus model with an A followed by an A. So everybody understand what this picture is doing here? Okay, so this is captures better what we know from sequence data than having two separate models. because the two separate models never really told you about transitions from one to another, and yet that's exactly what's happening in terms of the linear molecule. Okay? And I mentioned earlier this problem of where do you get the negative data from? If the negative data is just taken sort of from a sea of data that's not island data, how do you really know that that's relevant to the issue of when you see sequence that will have some islands and not have some islands? You really would like to know what the non-islands look like that are near the islands, or at least in a sequence that you're likely to have in your hand when you're looking for islands. So this model is richer and hopefully a better predictor because of that reason. This is, again, another question, sort of an open-ended type question I could ask on a final exam, which is sort of why is the hidden Markov model of the CPG island a richer, potentially richer, depends on what data you have in hand, a potentially richer model than having a model for the plus and a model for the minus and then using the log likelihood. Okay. Nonetheless, how do you use this? All right. Well, first of all, why is this a hidden Markov model and not a Markov model? Yeah.
I have a question.
Right.
In this model, do you include the transition probability from A plus to C plus to B?
Yes, right. Yes. Inside this box is this whole thing. I didn't want to write it down again. And inside this box is the plus model. And inside this box is the minus model. Okay. I didn't want to write all that, draw it out, and neither did the people in the book. They didn't want to draw all those arrows either. But yes, inside here, you have, I mean, that's presumably what's going to, most of your time is going to be, you're going to be inside one model, and then you switch to the other one, and you're inside that one for a long time, and then you switch back. Yeah?
The question is that in this hidden Markov model, we have a transition probability matrix 8 by 8.
Yeah, that's right. So there are 8 states here, and in this Markov model, you can move from any state to any other state. So it's going to be an 8 by 8 transition matrix if you want to write down all the probabilities. Well, let me just end again with this one question. Why is this a hidden Markov model and not a Markov model? Okay, so what do you do with this thing? You start somewhere. You emit a C. You move somewhere. You emit a G. You move somewhere. You emit a C, say. You move somewhere. You emit a T. You move somewhere. You emit another T. And the point is that from the emissions, you cannot tell from that alone what states you were in when you emitted them. And that's just because there are 2 states for C, there are 2 states for G, and so on. So you can't, there's no longer a one-to-one correspondence between what's emitted and what state you're in. And the key issue, I know I'm off west, but just let me plant this idea. The key issue in using a hidden Markov model is when you have a given sequence in hand, you want to find what's the highest probability, what's the maximum probability Markov chain through here that would have generated that sequence that you have in your hand. And when you look at that particular Markov chain, it will sometimes be up here, and those are the sequences, those are the characters that you'll say are in the CPG island, and it'll sometimes be down here, and those are the characters that you'll say are not in the CPG island. So next time we'll talk about when you have a hidden Markov model and you have a sequence, how do you figure out what the most probable Markov chain is that would have generated that sequence?